Hello everyone, welcome to lecture 8. From this lecture, over the next four lectures, we're going to talk about the signals and the signal processing techniques, especially what are the signals and how can we decompose it and how do we synthesize the signals, and also how to do the Fourier transform and doing some the frequency analysis and time domain analysis. In this lecture, we're gonna talk about the basics of the signals. You'll find this lecture note in the website. And today, we'll start from the basic mathematical concept. So the analysis of signal often involves the operation of trigonometric functions like sine and cosine functions. And the sum of this is because the signals can be decomposed and re-expressed with the trigonometric functions, sine and cosines. And the sum of multiplication and power operation of sine and cosine functions can be simplified by using exponential function if we assume the Euler's identity. So let's look at one example here. So this is the system that we are going to deal with, and xt is the input. So the xt with the black has the amplitude of b and the oscillation with the omega t. So that's this black line. Okay. And the output yt will have a different amplitude a and cosine, but it's a little bit delayed by delta t. So t minus delta t and times omega, right? So you can see that the amplitude of the x, which is the input, is b here, and it starts from b at 0 degree or at time 0, and it oscillates with some frequency. And here a is the output will have the same period, but it's a bit delayed. So t minus delta t is given here, and that's the distance. The difference time delay. So the delta t can be changed and expressed in terms of the phase angle phi. And to do that, if the period is t, and delta t over t, or the delta t to the t, will be equal to phi, the phase angle, to the 2 pi. So the period t, it corresponds to the 2 pi, right, in radian. So then delta t will be phi times t over 2 pi, and omega is 2 pi over t by definition. So then phi will be 1 over omega. The delta t will be phi times 1 over omega. So then if we put this one in the yt, which is a cosine omega t minus delta t, right? Then, and we want to express one, and here the omega t and omega times delta t will be what? Phi, right? So then phi, like this. If we use the trigonometric relation, then we can decompose into cosine omega t times cosine phi plus sine omega t times sine phi, right? And here a cosine omega t, a cosine phi times cosine omega t plus a sine phi times sine omega t. And here this can be replaced with this small a and small b, and then this will be the what? This will be amplitude, and this will be the another amplitude in orthogonal to this term. So then it will be like some complex number. Here is the a, here is the b, and this will be the real, and y-axis will be the imaginary number. And let me use, this is the a, and the angle will be the phi, the phase angle. So this is a plus j b. So then we can express this one, a cosine omega t plus b sine omega t, and we know that this part is in phase part, so it could be expressed in the real number term, and this is out of phase part. So that's gonna be the imaginary part. And then you can use the Euler's identity. You've seen this one before in the previous lecture. It's very convenient to use this Euler's identity. A ij phi is a cosine phi plus j a sine phi. And of course this can be a or this can be small b, so then it will be a plus jb. And so then if you have this kind of a signal, or the mathematical form for the signal, if you do the power exponent at the power exponent n, then because it's the exponential term, it will be simply, it can be easily calculated, right? And especially when the e to the j 2 pi k, so this number, the k is the integer, and I'm gonna repeat every 2 pi, then e to the j 2 pi times k, so then cosine 2 pi plus j sine 2 pi, and this becomes 0, and this is the same with 1, so then 1 plus j 0 or j naught, so this is 0, so then just 1, right? So then whenever there's an angle, if you subtract like 360 times integer, then it's gonna be the phase shift. So here j e to the j times phi plus 2 pi k, and then we can decompose this term and j times 2 pi k term, right? So then this will be like this, and we know that this is the 1, so that you have only e to the j phi remained, and that's the phase shift. So using this trigonometric relation and Euler's identity, then it will be more convenient and it's easy to deal with these complex numbers and the signal too. And this example, we're gonna do this one together in the lecture, in the class. So then, continuous signal and discrete signal. Practically most of signals are analog. It's continuous signal. But when we the save or the electronically load the signal and save it in your computer or the oscilloscope, and it becomes very digitized. So it becomes a discrete signal. Then if your index increases with time, like from 0, 1, 2, 3 to the I and to a certain number, then at each time, when the I is 1 and you have some amplitude, and when the I is 2, it will have a different also amplitude because it changes with time. When the I is 3, it will have some amplitude x3. So then this x1, x2, x3, x4, x5, x6, xi to a certain xn, it could be a one array, yeah? x0, x1, x2, x3, xi, like that. So the signals are now digitized into an array here, or could be an matrix. And there are even or odd signals. Even signals are symmetric across the y-axis. So when you fold it with the y-axis here, and it will be identical. And the example of that will be cosines. So mathematically, xi is the same with x minus I, and the example will be cosine function, right? And when it's odd signal, it's symmetric across the origin, so here. So then xi will be x minus I times minus 1. And one example will be a sine signal. So then these signals can be decomposed into sine and cosine, and the sum of these two, the combination of the sine and cosine. Today, in this lecture, we're gonna talk about the elemental signals. And for the elemental signal, there are impulse and step, sinusoid, exponential, and wavelet, and noise. Let's talk about the first one, impulse first. So impulse is like the definition of the impulse is delta I is 1 if I is 0, 0, and delta I is 0 if the I is not 0. So then if we draw this one, so this is the I, and when it's 0, it will be 1, right? So here it will be here, 1. And when it's 1, 2, 3, 4, right? It's gonna be 0, 0, 0, 0. And when it's minus 1, minus 2, minus 3, minus 3, 4, also it's gonna be 0, 0, 0, 0. So this is called the impulse signal. So then, can you draw, let's draw example, delta I minus 2. So delta I is this signal, right? So delta I is this signal. What about delta I minus 2? When I is 1 or 0, then delta minus 2. So this should not be 1, so this should be 0. And I is 1, so it's gonna be here, right? And when I is 1, and the delta will be minus 1, so it's gonna be here. When I is 2, delta will be 0, and delta 0 is 1, So here and 0, 0, 0, 0, 0. So it will be like, and this is delta I minus 2, and this is delta I. So this is called the impulse signal, and or impulse function. What about the step signal? Step function is when I is if the I is less than 0 or negative value, UI is 0. So this is UI. This is delta I. And when the I is the same as 0 or positive, then UI is 1. So it becomes like this here, right? 0, 0, 0, and 0, 0, 0, 0. And we can express this one as the sum of impulses, right? So that means that when you this will be the sum of this one, right? This is what? 0, 0, 0, 0, 0, 0, 0, delta I. And it could be 0, 0, 0, 0, 0, or 1, 0, 0, 0. So this is delta I minus 1. And the next one will be 0, 0, 0, 0, 0, 1, 0, 0. That's I minus 2. And you can go on, right? So then if you synthesize all the things together, say I minus 3, right? And then it becomes the sum of delta I from negative value, like the negative infinite, to the I. That's UI. Right? Good. So that's how you get the this function. So the step function can be expressed as summation of the sum of impulse functions. Okay. Third one is the sinusoidal, and sinusoidal here, xt is sine omega t plus phi, and in a discrete form, xi is sine omega ti plus phi. And here, let's put some, change this ti in a discrete form. So then ti will be I times delta t, and here the delta t is called the sampling interval. Right. So you can discretize the signals, getting the sample every second or every 1 microsecond or every 1 nanosecond. That will be the delta t. So the interval between the signal, the data. Then omega is 2 pi over t. Then omega ti will be 2 pi t I delta t, right? So 2 pi, and here the period is n times delta t. So n is the number of points, number of samples. Then n delta t times I delta t. So it will cancel out. So then it becomes 2 pi n I, right? So then if you put this one in here, then xi is sine 2 pi n I plus phi. So sinusoidal function is expressed in a discrete form. Okay. the exponential function is very important and it's useful to use. Here, let's say that this is the x and this is the I, or I times delta t. Then, no, when the b, here this will be the independent variable. When the b is positive, it will increase with I. And if the b is negative, it's going to decrease with I. And this is called the amplification, and this is called the attenuation. If the b becomes imaginary, so then we can use Euler's identity, right? So b is j, it can be expressed as j times omega, and the omega was before the 2 pi over n times delta t. Right? So then x I is a times b I delta t, and if you replace the b with this, then a times e j 2 pi n delta t times I delta t. Then delta t will cancel out. So then a e j 2 pi n I. So here j is the imaginary number and I is index, right? The one that's increasing with time. Huh? Here index. Imaginary number. Then this can be expressed with sine and cosine. Cosine 2 pi n I plus j sine 2 pi n I. Right? So it's going to be an oscillation of a signal. What about if the b is alpha plus j omega, and here the alpha is negative value? So then it's kind of combination of exponential function and the trigonometric function, right? So when b is just a j omega, it's trigonometric function like this, right? When b is just a real number, then it will be exponential function like this, because the alpha is now negative value, is going to be like this. So it will be something like this function plus this function, right? So then this becomes this kind of a attenuating signal. So here, this is e to the minus alpha I delta t when this is time. Time I is I times delta t. Right? X-axis is, right? And whole function will be like this one. A exponent alpha plus j omega I delta t. And this is very similar to what we've seen in the chapter 6, right? The equation 6.36, which was the ux, the displacement, is a times e minus alpha x, e j omega t minus kappa x, right? In a lossy media. Somewhat very similar. And fifth one is wavelet. Wavelet is called sync signal. And this is just you have a denominator 2 pi m I. So that have some modular function like this. It have a packet of wave inside this low frequency. And m is the frequency content. And one of the famous one, or the widely used wavelet, is the Morley wavelet, and this is expressed as this function like this. The last one is the random signal, random noise. It's uncorrelated in any scale of the independent time variable, so you cannot predict what the value will be for the next one. And it's called xi is r and d and a, when the a is the amplitude of the noise. Okay, next topic is the signal synthesis and decomposition. The signal can be expressed as the sum of impulses, and impulse signal is delta that we've seen. For example, if you have the discrete signal like this, this is the I is 0, I is 1, 2, 3, 4, 5, 6, 7, and the amplitude is what? X0, X1, X2, X3, X4, X5, X6, and let's say that this is Xi, so this is I. Then this one, that's when it's a I is 0, is expressed as x0. So his x0 is the scalar. X0 is just a number for the amplitude to express the amplitude. X0 times delta I. Then what about this one? This signal will be x1 times delta I minus 1. So that it becomes this delta, the impulse becomes 1, the value becomes 1 when the I is 1. And this one will be what? x2 times delta I minus 2. And it can go on and on, right? And then here, the last one will be xk times delta I minus k. So then, when we combine all of this, this becomes whole one signal, right? Then this can be capital X, I, and delta I minus k. And here x express the amplitude, and this delta express the time shift. Right? So this is expressed in an array form, right? And we can also express this one in matrix form. And that's why, okay, y is x. This will be the y, and this will be the A matrix, and this will be X matrix. And this A matrix do the same thing with this sigma, and this becomes with the xi. So then this will combine, and this will combine, this will combine, and this will combine, right? Multiplication and also the summation at the same time together. And if we use, how do we express this delta with this matrix A? Now with the I increasing from 1 or 0, 1, 2, 3, or the 1, 2, 3, 4 to a certain value n, and we can use the identity matrix, I matrix, that start 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. So only if you have a diagonal term 1, then this will become do the same with the this impulse signal, impulse function delta. This is n by n. So then so this is the same with xi is delta xk delta I minus k, a sigma, and it's called the I matrix. So the signals can be synthesized using the impulse signals and also using sinusoidal signal. Actually, all the signals can be expressed with the sine and cosine function, and this is the basic concept of the Fourier transform. So here the xi, this function, is expressed with the cosine and sine with the AU and BU. Here the AU and BU is the it tells you the amplitude at that frequency, and it's fitted to with the least square function, least square fitting method. There are others more, like you can have the a function decomposed or synthesized with this step. And there are other ways for the synthesis and the decomposition. Okay, that's it for the lecture 8, and thank you for listening.